It's so nice to be here. I love this venue. It's such a romantic venue. We're literally under the planetarium. I love it. This building has a special place in my heart. It's really nice to see everyone come out for science. Woo, science! Yeah, we believe in science. Science is great. So I wanted to talk tonight about this recent gravitational wave discovery. On February 11th of this year, an otherwise obscure experiment made an announcement that sort of made the entire world kind of freeze and pause for a second. How many people heard around February 11th about the gravitational wave detection? Okay, excellent. It was an amazing moment. I don't even think that the experimentalists expected the world to pay that much attention. After about an hour, how many people felt like they understood what the gravitational wave detection was about? Okay, yeah. Oh yeah, this one guy did. Yeah, it's very, very difficult to understand. And so I want to spend tonight picking apart what that discovery was, why it was so monumental, and why it was so moving. Even though very few people had heard about LIGO before that day, it cost 50 years of people's lives. Some of the original LIGO experimentalists started this in the late 60s when people didn't even know if black holes were real, when people didn't even know if gravitational waves were real. Einstein was arguing about the existence of gravitational waves for decades. He kept changing his mind. He famously wrote a paper saying gravitational waves do not exist, and then between acceptance and actually putting it to press, he snuck in a completely different paper that said that they did. So, he was sort of all over the place. And it's an incredibly difficult subject. So imagine starting this experiment in the late 60s, and now it's 2016. It's the centenary of the year, of the day that Einstein, or the year that Einstein first proposed the existence of gravitational waves, and they make this detection. So I really want to spend some time talking about what it all really means. So here it is. We're about to listen, and this is already something you should feel is strange. We're going to listen to the discovery. Okay? In astronomy, we look at discoveries. This time, we're going to listen to the discovery. It's going to play twice. It's going to play the sound of the gravitational wave recorded, and then it's going to increase it in pitch because the human ear does not do well with the lower notes. So you're going to hear it better the second two times. Okay, here we go. Want to hear it again? Okay, so in the second time, all that's happened is it's been falsely increased in pitch, and you could hear it again. Now, you should already be wondering why this giant machine, which spans 4 kilometers, of which there are 2 on 2 different coasts in the US, made a recording at all. Why didn't it take a picture like a telescope? And so that's what we're going to kind of spend some time picking apart. And why can we hear it? It literally lands in the human auditory range. So we'll talk about that as well. So what was the gravitational wave discovery about? So let's first start with what we do know. This is actually from the Digital Atlas here at the American Museum of Natural History. Compilation of known observations of the universe. Essentially, every object that has ever been observed is placed in this atlas. And then you can drive around the atlas if you want, kind of like Google Maps, only bigger. And here is a map, and this is not a cartoon or a simulation. It's a map showing what our own galaxy looks like. This is the Milky Way galaxy. It's a collection of 100 billion stars. We have never gotten this far outside of the Milky Way galaxy to take a look at it. This is some hundreds of thousands of light years from our current location. We have never been able to get there. Where we live is inside the Milky Way. So here we are. Let's go and figure out where we are in the location of the entire universe before we figure out how we observe it. We're coming inside into the spiral arms. New Yorkers are always very offended to find out that they actually live in the galactic suburbs. I know that's terribly disappointing. But it's better than the center of the galaxy because there's a supermassive black hole there. So, and we are slowly spiraling into that supermassive black hole, but it's 26,000 light years away. It will take a very long time. There's our sun. It's quite an average sort of yellow star. We have gotten not even this far outside of our solar system? Well, here we have. Voyager, which was launched in the 70s, just broke out of the sun's magnetic influence and is basically interstellar after decades. And that's the farthest we've flung anything in the universe. Here we are on the third rock from the sun. It's a very nice place, you may have heard. Good real estate, you know. And you just saw the great view we had of the galaxy. Okay, here we are. Most of us are bound to this rock. Very few of us have left this rock. Most of our satellites orbit this rock. Very few things make it away from the Earth or outside of the solar system. So everything we know about the universe comes to us from light, and that's already stunning. It comes to us as we receive light sent to us across the universe, and because it takes light traveling to us some time, the further away we see something, the further in the past we're looking. So we have a map not only of a universe 90-some billion light years across, but nearly 14 billion years old, and we get it all by taking pictures. You know, since Galileo first pointed a telescope at the sky, we've gotten this kind of silent movie. And what we're doing differently now is trying to detect something about the cosmos in complete darkness, in the absence of light. And to do that, we really use gravity. This is another, again, digital atlas. It's not a cartoon. Every object you see in this digital atlas is an entire galaxy. Okay, so there are as many galaxies in the observable universe as there are stars in the Milky Way. There are hundreds of billions of galaxies, each one with hundreds or more billions of stars. And although this is a lot of stuff that we've seen, most of the universe is actually dark. Okay? 95% of the universe is not luminous at all. It will never send us light. We will never see it with a telescope. The cosmos is largely darkness. We're lucky we can do astronomy now, you know, because the future is getting even darker. So here we are, and I didn't mean that as like a political statement or anything. Don't read too much into it, people. So here we are. What do we do with a universe that is largely dark when we cannot take pictures of the sky? We want to use pure gravity, and that's where Einstein comes in. So Einstein proposes his most radical, most important idea. It's finally written down beautifully in 1915. Did I say 1916? I lied, 1915. It's all right, you can look it up. Einstein once said, you know, he didn't know his phone number because why memorize something you could look up? So that's kind of how I feel about some of these things. So in 1915, Einstein writes down his most radical idea, the general theory of relativity. And in this idea, he expresses his entire theory of space-time. He says, and we're going to say it in one sentence very simply, that mass and energy, like the sun, curve space and time around it. So things fall under natural curves in space. If you think about, if I was floating in empty space and I were to throw my clicker, what path do you imagine it would take? I mean, totally empty space, no Earth, no nothing. What path do you imagine it would take? Straight line, because what else is it going to do, right? Straight line. If I throw the clicker in this room, what path is it going to take? You again. It's going to go down, okay? It is literally tracing for you a curve in the shape of space-time. It's a stunning idea. It's an absolutely stunning idea. Mathematically, it's very hard, but the intuition is obvious once you realize that it's my hand that's in the way of gravity right now. And once I let go, it's going to trace for me the natural curves in space-time. And so when the International Space Station is orbiting the Earth, it is falling freely along a circular curve in space-time. It's absolutely falling. It's just thrown so fast that it always clears the horizon. It never crashes into the surface of the Earth. But it's actually, the astronauts in the space station are falling. That's what they're doing all the time. So there's Einstein's theory in a nutshell. Not bad. Now you don't have to go to graduate school for 5 years. Here's the most extreme example of Einstein's theory. It's the black hole. Here's my portrait of a black hole. So in the same year that Einstein publishes his great theory, Karl Schwarzschild, who's an infantry soldier during the war on the Russian front, is between calculating cannon fire trajectories, starts reading the proceedings of the Prussian Academy of Sciences, you know, as you do, and solves for the curved space-time around a mass, pretending really, just as a fantasy, that all the mass is crushed to a point. It's not a physical or real solution. It's just an idea. Imagine that it wasn't the Earth, but everything was crushed to a point. He writes down this solution. It's very obscure. Einstein's very impressed with it. He helps him get it published, but Einstein thinks these things will never form. This is not reality. Nature will protect us from such strange things. The strangeness we now know as the black hole. It didn't earn its name until like the 60s, 1967, I believe. It earned a name from the famous relativist John Wheeler. So here is a black hole. This is not a cartoon. It's a mathematical model by a physicist, Andrew Hamilton, who does these stunning visualizations of black holes. In this computer simulation, a black hole about the size of our sun has formed. And if you took the entire sun and made it a black hole, it would be about 6 kilometers across. Okay? It would comfortably sort of fit in Manhattan. Right? 6 kilometers across, the entire mass of the sun. And what do we mean by 6 kilometers across? We mean that there's a shadow cast because the space is so strongly curved that even light takes a path that always points inward. There are no paths that point outward, no curves in space-time. Saying it another way, you would have to travel faster than the speed of light to escape from that shadow. If you were to go up to the black hole, there's nothing there. We have this myth that black holes are dense crushes of matter. Black holes are empty space-time. They're like places more than they are things. And here we're seeing a little model of the Earth, which is self-illuminated because the sun's gone. So the little model of the Earth is self-illuminated, and notice that it's looking very warped as it passes behind the black hole sun. And that's just an effect of the light following bent paths as well. So all of this is about the bending of light. Okay, we're almost at gravitational waves. So here, Einstein begins to think immediately, look, if the sun and the Earth and these strange things which don't have a name yet, we now call black holes, can curve the space and time around them, surely when they move, the curves have to follow them. And if the curves have to follow them, nothing can travel faster than the speed of light. So those curves must follow them at the speed of light. And what you create is like a wave, literally in the shape of space-time, in the curves you fall along as the objects move. So in this cartoon due to Ligo, courtesy of Ligo, you see how the curves in space-time follow the object. And if I have two objects moving, they create a wave in space-time. Those are the gravitational waves that Ligo detected. They're literally curves in the shape of space. If you were floating freely near the two black holes as they collided, you would like kind of bob on the wave like something floating on the ocean. Okay? And it would be darkness, complete darkness, but you would bob on the wave as it passed. Now we'll talk about what was exactly detected in a minute. So here's how LIGO works. This crazy idea, imagine it's the late 60s. Ray Weiss is a young professor at MIT. He's working on other projects, but he has this mad idea to measure these waves in the shape of space-time that people don't even know are real. People don't even think black holes are real. Black holes are crucial for the conversation because only the most cataclysmic events can ring space-time loud enough for anybody to have any kind of hope of detecting it. So you need something like the intensity of black holes, which as they orbit each other are like mallets on a drum, and they will literally ring space-time, emanating these waves outward while we wait to receive them here on Earth. Now, Ray's idea was kind of like in this cartoon. Imagine space-time is changing shape where you are. If you hang mirrors at the endpoints of this L-shaped instrument and you bounce light along the L-shaped instrument, the light will come back at different times because it'll have traveled different lengths as the mirrors bob on the wave. And in that way, you could record basically the floating mirrors and the bobbing wave. In some ways, LIGO is like the body of an electric guitar recording the shape of a guitar string, right? If you pluck an electric guitar, it technically doesn't make a sound. You attach it to the body of the electric guitar, and it records the ringing shape and plays it back through an amplifier. This is how LIGO works. It's like a giant musical instrument. As the mirrors bob on the wave, LIGO records the shape of the bobbing, and it literally plays it back through a conventional speaker system. Bear in mind that these are billion-dollar machines that they took 50 years to build, and now a team of nearly 1,000 people work on them, that they span 4 kilometers. When the light is going down the arms, each one of these arms is 4 kilometers long, and there's 2 of these machines, one on the coast of Louisiana and one in Hanford, Washington. So when the experimentalists are in the control room, they are literally listening to the detector. Let's take a look at the real LIGO. This is the real LIGO. So here are the long arms of the instrument. This must be Hanford. You can tell Louisiana because there are swamps along the sides, swamps. There's Louisiana. And there are alligators in the swamp, and mysteriously bass. No one knows how the bass got there. So you see these 4-kilometer-long arms. We're about to go into a cartoon where we're inside the tunnel. There's a laser that's shot down this tunnel, and the light has to travel the 4 kilometers. It's a powerful laser. This is a vacuum inside here. That vacuum represents the largest holes in the Earth's atmosphere. There's less stuff in the LIGO arms than there are in regions of intergalactic space. These are the beer chambers, as they're sometimes fondly known. There's not actually beer in them, but there are like the instruments, the mirrors, the suspension systems, and this is what the instrument sounds like in the control room. It just sounds like noise. It sounds like noise unless a signal hits. So there's one instrument on the Gulf Coast, one on the West Coast, and if something happens in the universe, some cataclysmic event that rings space-time, these waves will travel, and they'll travel all the way to the Earth, and they'll strike the instruments, the mirrors will bob, they'll be recorded, right? That's the aspiration. Now, in the year 2000, the first LIGO instrument was built and listened for 15 years, nearly, and heard nothing. Okay, so this was an incredibly successful technological achievement in the year 2000, and the skies were silent. And they needed to build an advanced machine. Then things like this happen, you know. The Hanford machine is on the same site as the plutonium separation facilities that were used for the original atom bombs. And so there's security patrols that drive around, apparently with a poor knowledge of geography, in the middle of the night, you know, no lights or anything, and crashed into one of the LIGO arms. Luckily, he didn't puncture the vacuum. If you ask the experimentalists what would have happened, they said we'd all go home. It's over. The vacuum was drawn in 1998 and has never been brought up to atmosphere since. The vacuum is punctured, the experiment would have been over. That would have been it. He broke his arm, but fortunately, not the LIGO arm. And it might have been like opening a vent in space. I don't know how deadly it would have been had he broken the vacuum for him. It's like opening a door on the space shuttle, but you know, the vacuum's on the inside, not the outside. There was also an incident in Louisiana where hunters started to shoot up the Louisiana machine. They said by accident, but people didn't really buy that story. One of the main experimentalists on the Louisiana site said, you know, the Europeans just think we're so American, you know. Now all we need is a hamburger incident or something like that. But we survived all of this. The year 2015 comes. They've taken out of the beer chambers, which you can separately isolate from the vacuum, and installed new components. They basically replaced everything but the nothing, everything but the vacuum. And by 2015, the machine was operational. That year in August, Ray Weiss, who's now in his 80s, who's on site all the time, said to me, you know, if we don't detect black holes, this thing is a failure. If you asked anybody else on the ground when or if we would ever detect black holes, they said not until 2018, 2020. Just don't even think about it. It's not coming anytime soon. Ray was pushing for the centenary. He's like, I want it, goddammit. Oh, Ray loves to swear, by the way. He loves to swear. I want it, goddammit. I want the centenary of Einstein's paper. You know, I'm pushing for it. But even he started to think, oh, it'll never happen. So here it is, it's September 13th. Ray's on site looking for radio interference, and a lot of the experimentalists are interrupting the machine. They feel they're not ready yet. So they decide to do tests. They're running these aggressive tests on the machine, postponing their science run. And these tests really disturb the machine. They really basically ruin any potential for detection, but they just didn't feel they were ready yet. It comes early Monday morning, September 14th, and in Louisiana, you know, a lot of young graduate students and postdocs working on this instrument at 4 in the morning. They get tired, they decide to go home. They put down their tools, they're done for the day. Same thing happens in Washington State. They were gonna run all night, but they just get fed up. They leave the machines locked, though, in observing mode. Within the span of an hour, this signal, which had been traveling for 1.3 billion years, I know it's crazy, strikes Louisiana, rings the machine there, is beautifully recorded, middle of the night, nobody's awake. Nobody hears it in the control room because it's too fast. It's like 7 or 5 milliseconds later, it cruises across the continent and rings the machine in Washington and is beautifully captured there. 8:30 a.m., Ray wakes up and looks at the logs, as he always does, and he thinks, what the hell is going on here? You know, what's this? And here's what they detected that morning. So this is a computer simulation of 2 black holes, each one about 30 times the mass of the sun. One was a little bit bigger than that, so they were big. We were surprised how big they were. One was maybe 29, one was maybe 35 times the mass of the sun. This is drastically slowed down so that we can watch it, but we caught the final few orbits where these 2 black holes, which might have been orbiting for 1 billion years for all we know, are in their final few orbits. These orbits took 1/5 of a second. That's what was caught by the instrument, 1/5 of a second. In that final 1/5 of a second, the ringing of space-time was finally loud enough for the instrument to record. They merge, they form one bigger black hole. It's about 62 times the mass of the sun. It very quickly sheds off its imperfections and goes quiet. I think we have to see that again because it's so beautiful. No telescope could see this event. It happened in utter darkness. And again, it's drastically slowed down. This means that the original LIGO instrument very well could have had these very gravitational waves passing over them when the black holes were further apart, going slower, but it was too quiet to detect. It was only the final 1/5 of a second that was loud enough because what LIGO measured was a deviation in the mirrors swinging over 4 kilometers of less than 1/10,000th the width of a proton. And it was not until they could do that that they could even catch that final instant. So there it is, that stunning result. So now what you should be listening to, I'm going to play you 2 different things. What you should be listening to when you're listening to the gravitational waves, you should be thinking, oh, it's like a ringing drum, okay? And that this instrument, the LIGO instrument's like a musical instrument that's recorded the shape of the ringing drum, and that's why we're listening to it, just like you listen to a guitar in some ways. And also you should be listening for the sweep up. The reason why it sweeps up is because the black holes go faster and faster as they get closer together, so the ringing sweeps up in pitch. And we're going to listen to 2 different detections, because on December 22nd, there was a second detection of 2 black holes colliding. On Boxing Day, 2 smaller black holes. And so we're going to listen to the Boxing Day detection and again the original detection from September 14th. And then we're going to hear them again scooped up in frequency, in pitch. And the reason we do that is because the human ear is not so good at the low notes. So here we go. The low notes are particularly bad on a computer. Okay. Kind of similar. Okay, is it going again? Oh, here we go, increased pitch. Yeah. Who thought black holes would sound like that? It's not what you expect, right? But it'll be your ringtone any day now. So when you think about how remarkable that was, let's think about that. These black holes came from somewhere in the southern sky. Right now, they've formed a big black hole that's dark and quiet. We cannot see with a telescope. We cannot find with a telescope, and we can't hear it anymore. And it's out there moving away from us with the expansion of the universe. And when we start to ask ourselves, well, how many are out there? We're already, once LIGO's operational all the time, we're going to start recording black hole collisions monthly, and now maybe neutron stars, other dead stars, maybe stellar explosions, maybe other kinds of collisions. But out here, this is the Hubble deep field, again, every one of those objects is a real galaxy. And this is a patch of sky about 1/10 of the moon. Okay, and this is how many galaxies we see. In every one of these galaxies, there might be 1 billion black holes. There's a supermassive black hole, millions or billions of times the mass of the sun, in probably every one of those galaxies. And so we're looking for this future, not just when we're going to be recording sounds of space, but maybe something we haven't even thought of yet. I mean, that's what we're all really after, in truth. You know, scientists love nothing more than the unexpected. Being confirmed right after $1 billion is kind of a drag. But with the first LIGO detection, we already made new discoveries. Those black holes were huge. We have never detected 2 black holes. We've never detected black holes that were completely dark. We've never detected gravitational waves. So it was like a clean sweep. But what we're looking forward to ultimately in the future and the life of the universe, when you think about where we're going, is we will fall into black holes eventually. It's going to take a very, very, very long time. But eventually, everything that can will fall into black holes. Eventually, all of those black holes will evaporate, as Stephen Hawking told us they must. They'll evaporate into radiation. And the universe will expand, and it will go both dark and quiet, which is why a friend of mine says we have to do astronomy now. But I think what we have to look forward to is really a remarkable future, and really what we're all hoping for. LIGO just came online, I think this week maybe. I've got to check in to do more detections, is what we've always gotten when we've done astronomy, which is something totally unexpected. Thank you.